So today's topic is about arc length of a curve. But the curve is a typical curve is here is a graph of function. The graph of function is a curve, right? I'm going to show you how to set up the formula. Okay. So first of all, there was a definition. How do we find the curve as the length of curve? So this is a graph of function, a special case. Okay. To find the length of the curve, you divide this into many pieces, right? And that's called P0, P1, P2, and so on. Here's the last one, Pn. So the length is almost equal to the sum of the length of this line segment. If it's a strict line, I can find the length, right? The length is actually the difference of those two vectors. Right? Now it's harder to see it, right? So how do you find the distance between the 2 points? Now, in case if it's the graph as a curve is a graph of function, okay, then this will be xi, and here's f of xi, right? Or let's just put a yi here. Okay, this is a point that has coordinates. Okay, yi, and this is a point xi minus 1, yi minus 1. So use a Pythagorean theory, and that is going to be xi minus 1 square and the yi minus yi I minus 1 square, right? Okay. And this is also, so this will be delta yi, the height, and this will be delta xi, okay? So that is going to be delta xi square, delta y square, okay? Then I take what is delta xi? You know, if we draw the line here, this is here's clear point, right? This is a x there, x1, right? And this is general one, xi minus 1, xi, okay? So if you view, if this is a graph of y equals f of x, so if it's the graph, if it is graph of y depends on x, so in this case, yi is going to be f of xi, okay? So delta yi divided by delta xi is going to be f of xi, right? Right, you take a look at this, right? So this is almost by the mean variance theorem. It's going to be, it is going to be, well, it's not almost, just an arbitrary. There's a point, okay? This is going to be the derivative of some xi star, okay? For some between those 2 points. All right, so you can replace, so then you can, what you can do, okay? So the length right now is approximated by, this is a calculus idea, how do you compute it, okay? How do you compute the length, you know? The idea is chop the curve into many pieces. And then the points each point has coordinates x, I, y, I. Then you approximate the length by the total length of this line segment. Okay. Now this time I'm going to take delta x out, so it's going to be. You can also take delta y out. Okay. So it's going to be delta y here, delta xi squared d and this is delta xi, right? If we take it up. But we know that this is going to be f prime xi star, right? Square delta xi. Okay, great. So this is viewed as like a function, okay? So the limit, okay, if we take the limit, if delta O at that cycle approaches 0, okay, that means you get more points on the curve. This limit is going to be the integral of the function 1 plus f prime x squared and dx, okay? So it's reasonable. Yeah, what is AB? AB is an interval, okay? So this is A, and this is the last one. Here's xn, which is B, okay? So the length, we get a formula. It's going to be the integral of the function. If this curve C is a graph of the function, a graph of function f. Now similarly, okay, if x equals g of y is between C and D, then the length of the curve is going to be integral from C to D, and this time is going to be g prime y squared plus 1 dy, okay? And you can get this formula by the same idea, okay? Now, we can also, formally, we can get a formula as follows, okay? Yeah. So I'm not just, okay. We can also think about, yeah, derive the formula using some ideas, similar ideas. Okay, so here's a curve, right? So this, take an arbitrary point here. You make a tiny bit of change called dx. You also make, okay, remember this, right? So here's tangent line. So this piece will be dy, okay? Okay, and then from here to here is called ds. So ds is going to be square root of dx squared plus dy squared. Okay. So ds is called the differential of the arc length. Okay, the differential of the arc length. Okay, ds is called the differential. Dx is called differential of x. Dy is called differential of y. S is the represent the arc length. So the length, the total length, this is curve C, is going to integral of ds. Okay, add them together. Okay. Then ds now can be changed to the dx squared plus dy squared. Then it's up to you whether you want to take x out or take a dx out. So if you take a dx out, you get dy dx squared and the dx, okay? Then you must have a interval here. Or if you take a dy out, so that will be dx dy and a dy. Okay, so there are several formulas. Later on, maybe we can describe the curve using parametric equations. In that case, see, so here's a curve, right? You can also describe this point and view this point as a moving object in space. So you're going to, x is going to be x of t, y equals y over t, right? So if in that case, okay, and when t changes, t is less than between alpha and the beta, okay, then you get to the whole curve, right? So if that is the case, then dx is going to be x prime t dt, dy equals y prime t dt. So when you put into that formula, so the length can be square root of dx, right? Still, this is very general. Then you take, what you're going to do is you're going to divide by t, dt, and you put a dt here. So this is alpha to the beta. So there's another formula for you to use to compute the length. So this is another way to derive the formula for the length of the curve. Okay. But more precisely, how do we get this formula? We use the approximation. Okay. And how do you find the length, right? What you do is you suppose this is a curve right on the ground. How do you measure it, right? You just pick up many points along the curve, and then you measure the distance, direct the distance between the nearby 2 points, and add them together. Okay, and the curve is almost a straight line between 2 nearby points. So you just use a straight line to approximate the distance, then add them together, then you get a total length. And those points corresponding the points on the x-axis and also the corresponding points on the y-axis. Okay, those are points denoted by x0, y, x1, x2, x3, xn. But this is by the Pythagorean theory, and you can translate, this is distance between 2 points, nearby points, and into a formula, right? So it can be computed by the formula used by the Pythagorean theory. And then you end up with something like that, and then depend if the curve is described as a function of f, as a graph of f, then the yi is determined by f of xi. Okay, then you end up with this type of a sum, Riemann sum of a function square root of 1 plus f prime x squared. So the limit should be equal to this integral. Okay. Now, if xi equals yi, then in that case, xi is going to be g of yi. Okay, and by similar argument, you will get this formula. Okay. Okay, so that's it. And formally, you can derive the formula using this. You don't need to partition the curve into many points. Okay, you just draw the picture, draw a tiny bit small triangle, and the one side is dx, the side dy, and the hypotenuse is ds. ds is going to square root of dx squared plus dy squared. This is still a Pythagorean theory. Okay, and then the integral means add all the ds together, right? So you get total length. That's right. So you get a similar formula. But the curve can be also described by parametric equations. Think about this is the curve is in the orbit of a moving object in the space, right? So the orbit can depend on time t. So you have two equations, two formulas for the x and y, right? Two expressions, yeah. Then dx is x prime t dt, dy is dy prime dt. Then you get another formula. For all those formulas, they have an advantage, disadvantage. Okay, so it depends on the problem. Okay, so let's take a look at the length of the curve. Okay, let's try to set up an integral, okay, for the length of sorry, my pen is pretty sensitive. For the length of the graph, as this graph is y equals sine x. X is between 0 and pi. So I'm pretty curious about this sine curve. Okay, we know the area, okay, and the region. We know the area, right? The area is going to be integral of the function, and which is going to be integer. because this is going to be negative cosine x evaluated to the endpoint. Then you get negative cosine pi plus cosine 0, which is 2. It's integer. So area is integer. And how about the length? Right? The length. So this is y equals sine x. So the length is going to be integral from 0 to pi and 1 plus dy over dx squared. Right? We already derived our formula. Yeah. Dy over dx squared. Okay. So let's see if we are able to dy over dx, so cosine square x dx. Okay. I'm not sure we are able to evaluate. 1 plus cosine square x cannot be, you cannot get rid of the radicals. Okay. So I don't think we're able to evaluate, but you can approximate and using, we already learned how to approximate the integral, right? So this is a good example. You can use that, and it can make a program for the computer if nobody has done yet, right? Then approximate. The computer can only do the multiplication, addition, right? Subtractions, but you can do this basic operations. Okay, then you write a program so the computer can approximate. Yeah, this is the integral. So that's that is yeah. Now yeah, we are not able to evaluate this integral. Okay. So now I'm going to consider the curve. Okay. Consider the curve y equals natural log x. So let's assume that x is between 1 and how about e? Okay. So let's draw the graph. Okay, let's draw the graph. Okay, so this is a graph. Here's the e, right? So this is e and the 1. That's a 1 and a 0. Right? Set up an integral for the length of the curve of the graph. Okay. All right. There are a couple ways to do it because this is this curve is the increasing curve, so it can be viewed y equals x. Eventually, x also equals e to the y. So actually, we're going to have two integrals here this time. I'm going to show you. If you view it as a graph of natural log x, then the length is going to be integral from 1 to e, right? Then the derivative of y dx. Okay, let's see if it looks simple. So the derivative of y with respect is 1 of x. Okay, I'm not sure we are able to even evaluate. Okay, sometimes sometimes yeah, you can evaluate, sometimes you cannot. Okay, so simplify it a little bit. You can take a you can take a x out, right? So I'm not sure we're able to evaluate. If we have to do that, I think we should try and use integral as trigonometric substitutions maybe. Okay, we can do this later. Okay, or this can be viewed as a graph of x equals e to the y. Then here's dx dy, and the y is from what? From 0 to 1. Yeah, look at the graph, right? Y is from 0 to 1. Here's a 0, here's a 1. Okay. Y is from 0 to 1. All right, so now x is e to the y, so it's integral of e to the y, that's e to the 2y, and plus 1 dy. Yeah, I'm not sure we can evaluate this integral. Okay. Now, let's see. Look at the book, back side of the book. If we can find a table of an integral formula from there. I think yes, we do have. Okay, you look at by the formula 32, no 23. 23. I read it in reverse order. Okay, in the table of integrals. Okay, so antiderivative. This is going to be negative square root of x squared plus 1 over x plus natural log x plus 1 plus x squared. Okay, and plus constant. Okay, so wait a minute. This is no, I copied the wrong. I copied 24. Okay. Yeah. Okay, let's say 23. It's the square of x squared plus 1. Okay, minus natural log 1 plus x squared and x. Yeah, that's correct. Okay, so using that formula, you don't need to waste time, to evaluate. So now our length is going to be integral from x1 to e, right? So I'm going to evaluate the two endpoints. So let's look at it. It's e squared plus 1 natural log. Okay, unfortunately it's a very bad number. And minus, it's a 1, so it's a 2. Natural log 1 plus square root 2 and 1. So not big a deal. Okay, so that's it. This is it's a number, right? This is about the length of the curve. Very strange number. Yeah, but you can evaluate. Some graph looks very nice, but the length, it's if it can express in terms of some well-known numbers, it's horrible. It looks horrible. Right. So now let's try to find or setup. Okay, we know setup is the length of the circle. Okay. All right. So here we're given the curve, but that curve is going to be a circle. X squared plus y squared equals r squared. R is greater than 0. I tried to find the length of this circle. Of course, we know that the circumference, total circumference, it's a 2 pi r. We know that, right? So the question is why this is true. Right? So now we can use the calculator to find. Maybe we can find this formula, right? We learned that when we were in the middle school. We were told that this. Some students already know this formula in fifth grade, fourth grade. Okay. The question is, how do you prove that, right? It's not like an area formula for the triangle. You can use the definition of the area for the area of the rectangle to derive it easily. For circles, such things like that, simple graphs. We are not able to use elemental mathematics to derive the formulas for the area, for the parameter. All right, but this circle is symmetric in all the directions. So the circle can be described as a curve of graph, right? So this one at the bottom is square root of r squared minus x, right? And the one on the top is square root of r squared minus x squared. So the length, which is called circumference, is going to be twice of twice of the length of a semicircle, right? The semicircle, up semicircle, it's from negative r to positive r, right? Square 1, square 1 plus dy over dx square and dx, right? You can use this formula to set up the integral. I'm not sure we're able to evaluate, but let's set up the integral. Okay. Now, when you differentiate dy over dx, this is a square root. So dy over dx is going to be, let me write down the formula, okay? It's going to be, okay, we have this part, then we have an x, so it's a negative x actually. Okay, you can find the derivative because it's square root of r squared minus x squared. Okay, I'm pretty sure this is correct, okay? And then when you square it, you get, here's x squared, here's r squared minus x squared dx. Then you combine those two terms inside, the x squared is gone. So you will get just r squared, here's r squared minus. Okay. So what I'm going to do, I is a positive number, so I take the I out. Again, you can find the formula in the back side of the book for this integral. Now, if you try to use you can also use a substitution by itself to find to find the antiderivative of this function. So I'm pretty lazy. I don't want to do that right now. So our main purpose is not to evaluate the integrals here. So I should have a formula somewhere sitting there, right, in the book. And just copy it. So there it is. Haven't found it. Just a minute. Just a minute. Okay. Well, unfortunately, it's not a given in the book because this is a very simple one. Right? If not, then you have to, if you cannot find it from somewhere in the book, then you have to do it by yourself, okay? Now, they're given, here give a little bit more complicated one, not this one. So this one, you have to use substitution, okay? So let x to be r sine x, sine theta, for example, right? So theta is between, I think it's better for cosine because you want x's run from negative r to positive r, right? So even you can use a cosine, okay? Cosine, well, no. Sine, yeah, let's try use a cosine, okay? Right, if you use a sine, that's fine, not, okay, then no, you have to let that r, see when theta runs from one end to the other end, x should be run from negative r to positive r, right? So that means theta should be equal from negative pi over to the positive pi over 2, right? Then when theta equals, then x is between negative r and the positive r, right? Yeah, that's good. Okay. So let's put it inside. So it's negative pi over 2 to positive pi over 2. And here's r squared minus r squared sine squared theta. And dx is r cosine theta d theta. Okay. Not too bad, right? And then you have this in the denominator. Then you get this is r, not pi, 2 pi, it's 2r. Then you have r canceled out, and this inside the square root of it's actually a square root of a cosine square theta, cosine theta d theta. okay? Because cosine theta is going to be positive number, okay? For a theta between negative pi to positive pi 2. So they're canceled out, actually. It's just equal to 1 to theta, okay? And then the integral from negative pi 2 to positive pi 2 is just pi. So that's why you get 2 pi half, right? Now this is a, this is a formula. This is the length of the whole circle, the arc length of the whole circle. Okay. What are you talking about? Number 16. Oh, the formula. I see. I didn't see it, but let's do this, right? So we got it. Use a simple substitution. Okay. All right. There's actually another way we're going to learn later. Is if you use a parametrization of the circle, okay, you can use this theta, okay. So x could be equal to r cosine theta, y equals r sine theta, and theta is between 0 and 2 pi. That's a simple. That's maybe polar coordinates, right? So simple parametrization for the circle. When theta changes from 0 to 2 pi, you get the whole circle. So remember, right? So the integral as a length is going to be the integral from, first of all, it's just dx of dy square, right? But if you divide each side by theta, then you get dx over d theta square, dy over d theta square, and d theta, right? So theta is from 0 to 2 pi. But this will be very much simpler because dx d theta, the derivative, right, is going to be r negative sine theta. Here's r cosine theta when you differentiate square d theta. And the inside is just sine square theta plus cosine square theta, which is going to be 1. So just r square. And the square of r square is r, so it's r. Then you have a 2 pi. So that's a quick way. So sometimes if you use a parametric equations for the curve in the xy plane, you can quickly evaluate the integral, okay? And then solve the problem. All right, so let's try another one. Find this time we have to find out, not only just set up an integral, okay? Find the exact length of the curve. Okay, the curve is given by y equals x to the fourth power over 8 for x square, and the x is between 1 and 2. Now it's harder to draw it. Okay, it's harder to draw it. Let's figure out the starting point and the end point. Okay. Right. So when x equals 1, what is the y value? Y value is 1 over 8 plus 1 over 4. I think it will be 3 over 8. It's a small number, right? Okay, let's try another one. X equals 2. Y equals 2 to the fourth power over 8 plus 4 times 2 squared. 2 to the fourth power is a 16 divided by 2 is 2. And this is going to be 1 over 16, right? And it's a pretty small number. It's close to 2. It's close to 2, okay? It's close to 2. So it's a 2 and a 16, right? But we don't write the 2 16. We usually prefer write 33 over 16. Okay. So one point here, it's 1, 2, 3, 4, 1, 2. Okay. And the first point is somewhere here. Okay, second point is somewhere here. It's close, slightly larger than 2. So curve is like here. It's not a straight line, but it's going up, right? Why you have to draw the graph? Because you get a pretty good idea how long this curve, right? It's almost a straight line maybe, but the length cannot be too big, right? The length cannot be too big. I'm pretty sure the length is smaller than 2 square root 2, okay? But yeah, it's not a line. It's very important to know that because sometimes it's in computation as well, okay? All right, so let's try. Eventually we have to find the derivative. So let's find the derivative first. Okay, I'm going to differentiate with respect to x. So it's 4 over 8 x cubed minus 2 over 4 x to the negative 3, and that is going to 1/2 x cubed minus 1/2 x to the negative cube. Okay, that's great. So 1 plus dy over dx squared is going to be 1 plus 1/4 x cubed minus x to the next cube squared. Okay. Now, when I square it, I get x to the 6th power minus 2, yeah, plus x to the negative 6th power. Okay. But 1 minus 2 over 4 is going to be positive 2 over 4. So this simply you get this. And then you immediately should know that this is going to be quart here x 6 to the 6 plus. So you can write it as a square. Okay, that's a very important observation. Okay, we needed that to simplify the integral. So the length is going to be x is from 1 to 2, right? This is what the formula gave to us. But now we know that inside the radical, it's a square of something. Okay, so you can get rid of the radical, then you can evaluate the integral. We're pretty lucky for this problem, so it's okay. Then you find the antiderivative of each term. And let's find the antiderivative of the first term. It is going to be quart of x to the 4th power. The second term, I think it's yeah. You can quickly write down the antiderivative. When you differentiate, you get x to the negative 3. Okay. Okay, evaluate two endpoints. So let's try. The first one is 2 to the 4th power, and then 1/2, 1/4 minus 1/2. Okay, let's simplify a little bit to see if it is a large number. All right, that's a 4 and 1 over 8 minus negative 1/4. Okay, so let's continue. 2 minus 1 over 16 plus 1 over 8. Okay, 1 over 8. It's going to be 1 over 16 here. So the answer is 2 and 1 over 16. Okay. So this is a number, yeah, it's pretty reasonable number if you look at the picture. Okay. This is the length, and we find it's a fraction, so it's a very nice number. So let's try another one. I hope you can do it. Okay, I'll give you a little bit of time to try. Okay, I'm going to set up the integral for you to see if you're able to evaluate the integral. So it's going to be from 0 to 2, right? And yeah, are you able to evaluate this integral? First of all, you write down the formula for the length. Okay, and then trying to evaluate this integral. Okay, please do it. Okay. Are you able to evaluate this integral? So very similar to the last problem. Right. So you can get rid of the radical if you can. Maybe. Okay. If you cannot, you have to use kind of substitutions. Okay, so let's see. So this is the integral, right? It's 1 plus. So derivative of a dy over dx is going to be just negative. It's positive now. Square dx. All right. Then, well, what I'm going to do is this integral. I can simplify it, right? It looks like this. E to the x c, right? So combine them into, yeah, let me redo it. Okay, it's 1 plus e to the x squared, right? I try, I hope I can get a square, but it's impossible. So I get, what I get is e to the x plus 1 over e to the 2x. I can only take the denominator out. Okay. I still have a problem with the radicals. I cannot write e to the 2x plus 1 as a square. Right? What I'm going to do, I use a substitution. Okay? I try to use a substitution. I let u to be e to the x, and then du equals e to the x dx. It's not too bad. Okay, so when x equals 0, it's e to the 0 is 1, and here's e squared. Okay, so get here's u squared plus 1, and this is a u. And what is dx? Dx is going to be, yeah, this is u and dx. It's a du over u. Finally, I got okay. Then I'm not going to waste time to evaluate this integral is a substitution, another substitution. I turn to the back side of the book and I try to find a formula to see if I can get one. Okay, yeah, okay, last time then somebody gave me the formula here over there. But now I have a formula, yeah. And this is a 24, right? 24, great. I have a formula, 24. So the 24, I copy it. It's going to be 1 plus u squared and u plus natural log u plus 1 plus u squared. Okay, so evaluate the two end points. Okay, and you do get the exact value, but a very complicated exact value. So when you square here, all right, and this is going to be e to the 4th power 1 natural log e squared 1 plus e to the 4th power. That's the first part. the second part, when it's 1, right? Right, that's the second part. Right, it's the exact value, but it's very complicated exact value. Right, but we can evaluate. All right, so now let's look at the next problem. Okay, we are given equation just like x squared y squared. X squared plus y squared equals r squared. The equation for the circle here, y cubed equals x squared. So we are not given the function. We are given the equation. Okay, so this equation determines the curve. Maybe the 2 pieces, or we don't know. So find the length of the curve. Okay, from the point -1 to 1 to 8 and 4. Maybe there's only one curve here. So let's draw the graph. Okay, the graph. Yeah, let's look at. Okay, so where's my file? Shoot. Okay. All right. We don't know the graph, right? So but we at least have found the 2 points. And the one is here, the other one is there. And I think the graph passing through the origin. Okay. It turns out to be, you want to draw the graph. There are a couple ways to do, you can solve for y, then you get x to the 2/3. So this is defined for any x, but there is a cusp here, which is origin. So the graph looks like that. 2 pieces. It's a symmetric. X can be negative. Okay, because this is going to be x to the 1/3 and the square. So the third root of x is defined for any x, and squares, of course, are always positive. That's why the graph is about the x's. So it's not a smooth curve. Okay, it is not a smooth curve. The function is not differentiable when x is the origin. Okay. But anyway, so you view y as a function. Yeah, you view the y as a function of x, then the length is going to be the integral from -1 to 4 to 8. It's 1 plus dy over dx. Let's set up all those possible integrals to see which one is easy to evaluate. Okay. When you differentiate y with respect to x, I get 2/3 x to the -2/3 squared dx. Then I get, there's a single point. This is the improper integral, turns out to be. Okay. So it's going to be 4/9 x to the 2/3. Okay. This is an improper integral, and you have to divide, improper integral, you have to divide the integral into 2 parts. Okay. So I can simply write this. Okay. Yeah, wait before we try to solve it. Okay, another way is you solve for x in terms of solve for y, right? So y cubed equals x squared. So x is going to be plus minus y to the 3/2. Okay. And in that case, if you want to evaluate, you still have to use a two yeah, you find the length of these two pieces. Okay, so the length, okay, is going to be this one, L1. This is L2, right? L1. You see what is y? And when x equals when x it starts from 0, as both are 0, right? So here's -1 and 1. Here's 8 and 4, right? Okay. When x equals 8, y is 4. Okay. So the integral for the first one on the left, and I think we're going to use a dy. So it's a y is from 0 to 1, dx over dy, square plus 1 dx dy. And that one is from 0, y is from 0 to 4, dx over dy square plus 1 dy. Okay, so what is dx over dy? Dx over dy is going to be, depends on sign, right? It's a plus minus 3 over 2y to the 1/2. Okay, so when you square it, you get 9 over 4. It's y plus 1 dy. Okay, and this one is from 0. Here's 9 over 4y plus 1 dy. It's not too bad. This is a linear. Okay, the substitution could be very simple. Okay, so you can let this one to be u. Okay. I think it will be much easier to evaluate the integral than the other one. So that's why I wanted to try both methods. Okay. Okay. And it will be much simpler, okay, if you do this one. Okay. So so let u to be 9 over 4y. Right? Of course, du equals 9 over 4 dy. And when y equals 0, right, this integral, let's figure out the first one. And when y equals 0, u is 0. When y equals 1, u is 9 over 4. And here's u to the 1/2. And the dy equals 4 over 9 du, okay? All right, so I take the constant out. So antiderivative of u to the 1/2 is, I think I'm getting u to the 3 over 2, so I should put 2 or 3. All right, so antiderivative of this function. All right, so here's 27 and 8, and then 9. Yeah, this is a 9 over 4, 3 over 2 minus 0. So 9 over 4 to the power 3 over 2 is going to be 3 over 2 cubed, right? 3 over 2 cubed, I think it's just equal 1. Yeah, cancel it out. All right, so it's just 1. The first part is just 1. The second part, slightly similar, 0 from 0 to 4. Okay, same substitution. Oops, I wrote too fast. Same substitution, but this time when u equals, did I make mistakes? I think I made mistakes. No, yes, no, yes. I made mistakes, okay? Because u is, there's plus 1 here. Okay, plus 1, sorry. That's why I can. All right, I have to correct it. Sorry for that. I did too fast. When y equals 1, this is plus 1, this plus 1, okay? So it's not that simple, this, yeah, I think it's correct. So it's going to be 9 plus 1 is 13. 13 over 4, 3 over 2. That's 1. Okay, so it's not a good number. Okay, similarly, this is when y equals 0, this is when y equals 4. It's going to be 4 cancels out. 9 plus 1 is 10. Square root 10. Okay, and here's a 4 over 9 u to the 1/2 du. Okay. Okay, so that is going to be antiderivative here. Yeah, it's 4 over 9 and 2 over 3 u to the 3 over 2 and then and this. Okay, then you plug the number and that is square root 10 to the 3 over 2 and minus 1. Okay. Right, so yeah, so that's what we got. Okay, I think it's a substitution much simpler if you use the second version of the integral. All right. Okay. Yeah, in many cases, okay, the problems are given to you. You can evaluate integral. Okay, so there are two types of integrals you can get. One is you can get rid of the square root, so you can evaluate it quickly, or you have to use a substitution. Okay, and you have to use a substitution to simplify the integral. Okay. So let's do one more example and we're done. All right, so here's a function, a chord of e to the x, e to the negative x. Find the length and the area and the function. Okay, and the graph. And let's try to. So I'm going to. I guess yeah. Find x is between. Now x can be between 0 and 1. That may be, or I have to put the natural log of 2, for example. Okay, make it easy. Okay, so this is a positive number, natural log 2. Okay, find the length if possible. Yeah, we don't. Yeah, find the length. And the area is much easier. Okay, so this is I'm not going to find the area, just find the length. Okay. Of the graph y equals f of x. Okay. Right. Yeah, we don't need to sketch the graph. It's not necessary. All you have to do is write down step 1. Write down the formula you can use. Okay, it's from 0 to natural log of 2. And that is going to be f prime x squared dx. Okay. Okay. Then you differentiate. So you get quart of e to the x minus e to the negative x and square. Now, my experience tells me when you see something like that, one term is e to some power, right, to the positive term, x, and another term is e to the negative x, and there's a minus in between them. Definitely, I can, without even thinking, I'm pretty sure this part is going to be this. Okay. So then you can evaluate. Right? Can get rid of the radicals. Okay. Then you find the antiderivative. Okay. There's very many simple problems like that. Okay. As long as you see a negative sign there, and then you can change it to positive. But we can verify this later. Okay. So I just say I can even write down I can get rid of the radicals quickly. So then you find the antiderivative of the first one, then the second one. You come back to that function again. Okay, now well, we have a problem here. Yeah, I did not set up the. Let me see. Do I have? Yeah, it's quite. Yeah, it's okay now. Yeah, a quarter of e to the natural log of 2 minus e to the natural log of 2 minus a quarter of e to the 0 minus e to the negative 0. Okay, so let's simplify the first one. E to the natural log of 2 is 2 minus negative natural log of 2, you know, right? This is e to the negative natural log of 2 is e to the natural log of 2 to the negative 1. That is going to be 2 to the negative 1, right? And minus a quarter minus 1. All right, this should be a positive number. Otherwise, there was a mistake there. It's 1/2 minus 1/2. Great. So that is 0, right? And the minus 3/4, so negative 3/4 is positive 3/4. So answer is just 3/4. Okay, this is a positive number. Okay. Yeah. So in mathematics, there was a interesting formula. When you have x plus or minus, right, and then you get 1 over x, it's a square, that'll be x squared plus 1 over x squared and then plus 2. So that's minus, that's 2 here. So yeah, this is that canceled out in the middle. Okay, so if I have a 1/2. Okay, let me check. So a quarter of x plus 1 of x. Okay. Now if I change the sign, okay. Let's see. If I put a negative sign here, usually it's negative. Okay. Then I have a negative sign here. So when I square this, okay, I do have when I change the plus minus, right? So this is plus. Then I get 1 over 16x squared. Then the product of those 2. So the product 2, yeah, this is 1 over x squared. The product 2 get minus 1/2. Okay. And when I change it to positive sign, and it's positive 1/2. Okay. So that means, if I add 1 to both sides, then negative 1/2 plus 1 becomes positive 1/2. So that's why you can have 1 plus 1 over x minus this is going to be 1 quarter x plus 1 over x squared. Okay. Okay, so we have to practice like that. Okay, so whenever see that negative sign, maybe more likely you're going to get a square. And also another one is distribute, yeah, it's 1/2 of x plus half of x. Let's try this. So it's going to be 1 plus 1/4 x squared. But when I multiply this out, 2 multiply 2, it's actually, right? It's going to be negative 1/2. You see, negative 1/2 plus 1 becomes positive 1/2. So those two combined, right? If it's positive 1/2, you are going to get half of x plus 1 over 2x squared. X over 2 is 1 over 2. Okay? So we have two versions of formula. Okay, let me summarize it. I can write like this. Okay. Another one is okay. So this is a 2. Okay. So if you see e to the x over 4 plus e minus e to the negative x, which is 1 over e to the x. Right? And then it's similar to the first formula. So it's going to be e to the x over 4 plus e to the x squared. Right? Yes. And then if it's 1 plus y cubed over 2 minus 1 over 2y cubed square, right? And that is going to be the second formula. That will be y cubed over 2 plus 1 over 2y cubed square, right? Great. So you can, I can create many examples like that. So 1 plus, 1 plus, or I can use square root, right? 1 plus square root x over 2 minus 1 over 2 square x square. That's going to be square root x over 2 plus, right? Then you can get rid of that. Okay. So how can I get a function? If I make an example for you, what I'm going to do is, I just this dy over dx should be equal to, right? So it's half of x to the 1/2 minus half of x to the negative half. So what is y? Y is the entire derivative of 2 over 3, right? And minus, and this is actually is a plus, right? It's minus x to the 1/2. Okay, when you differentiate, I get that. So using this example, okay, then I can always ask you to find, I can set up an example like find the exact length of this curve determined by, okay, and the x is, I can say x is between 1 and 4. Now, then you will wonder, how do you know this example? How do you create this example? I create an example like this. Okay, so I guarantee you I can guarantee you to get rid of radicals. So I just show you example how they are make up of those examples. Okay, so the length is going to be the integral, and from 1 to 4, and 1 plus dy over dx squared dx, right? When I differentiate, I end up with something like that. Okay, okay. So I already show you how to do that, right? And the square of x over 2 minus 1 over square x. So I guarantee, yeah, you can get rid of okay. Then oh, there's no 1 here. It's already, you know, the 1 is gone. Okay. So I can get rid of the radical. Okay. So I get half of square x. Then I can evaluate this integral. Okay. So let's do it again. Here's 1/2 plus 1/2 x to negative 1/2 dx. So the antiderivative of this function will be 3 over 2 or 2 over 3. And here's 1/2 x to 3, 2 over 3, not 3 over 2. Please. Okay, and plus x to the 1/2. Right? So x to the 1/2, when you differentiate together. Then you plug a 4, and the 4 to the 3 over 2 plus 4 to the 1/2 minus 1/3, 1 plus 1. Okay, so let's evaluate this. 8 over 3 plus 2 minus 1/3 minus 1. So I got 7 over 3 plus 1. So it's 10 over 3. So you see the length is 10 over 3. But how do I get this? How do I make this example? I just tell you the secret, right? This is how do I make an example. I use this one of these formulas. I use one of that. Okay, and I can replace x by e to the x. I can replace x by y cubed. I can replace x by square x. Then I solve for, because this is the area where you put a dy over dx here, right? Then I solve for y, and then I make an example. Okay, so then I can make lots of examples. Okay, so then I ask you to find the length, and it's guaranteed you can get rid of radicals. Okay, using, because this is a minus sign, then quickly can become positive sign and square. No 1's there, right? So there's no 1 being found out. Then you can, that's why radicals and square cancel out. That. Okay. So that's it, and I'm done with a quick with a lecture. Okay? So that would be quiz next week.